In this lecture, we're going to begin chapter 4. We're going to start talking about energy conservation for open systems. We're going to start with the conservation of mass for control volume or open system, where this is our system, the dashed line is our boundary, and we now have mass flowing in and out. When the conservation of mass principle is applied to the control volume, it states that the time rate of change of mass contained within the control volume at a given time t is equal to the time rate of flow of mass in across the inlet minus the time rate of flow of mass out across the exit. If we put some symbols down, we'll have our rate of mass inside of our control volume is equal to our mass flow rate in minus our mass flow rate out, where the dot above them denotes it's with respect to time, and that's how we denote mass flow rate. The units of mass flow rate are kilograms per second or pound mass per second. In general, there can be several locations on the boundary through which mass enters or exits the system. We can account for that by summing them. So if I have multiple inlets and outlets, the change of mass within my system is equal to the sum of what goes in minus the sum of what goes out. So what does this really mean? So if we assume we have some quantity of matter flowing with a velocity v across an incremental area at some interval of time, the amount of mass that crosses our differential area during that time interval would be the density of our material times our normal velocity times the amount of time times our differential area. If we were to divide both sides by time and taking the limit as time goes to 0 to get our instantaneous mass flow rate, our instantaneous mass flow rate becomes our density times our normal velocity times our differential area. If we were then to integrate over an area A through which the mass passes, we get the following expression for mass flow rate, that our mass flow rate is equal to our area integral of our velocity, of our normal velocity times our density times our differential area. So we're going to look at some forms of the mass rate balance. When a flowing stream of matter enters or exits a control volume, it has to adhere to a few idealizations, and then we can call our flow one-dimensional. The first idealization is the flow is normal to the boundary at locations where mass enters or exits the control volume, so we don't have mass entering or exit on an angle. All intensive properties, including velocity and density, are uniform with position over each inlet or exit area, so we don't have a non-uniform velocity distribution entering our system. If we follow these two criteria, we have what we assume is one-dimensional flow. So for one-dimensional flow, our mass flow rate is equal to our density times our velocity times our differential area. We can also write this in terms of specific volume. If we recall that our specific volume is 1 over our density, we get our area times our velocity divided by our specific volume. The product of our area times velocity is given our volumetric flow rate v dot. Note it's given the symbol v dot and not q, so not to be confused with fluid mechanics. The units of volumetric flow rate are meters cubed per second or feet cubed per second. If we were to substitute our new equation for mass flow rate back into our expression for the conservation of mass, we're going to get that the change in mass in our control volume with respect to time is equal to the sum of what comes in minus what goes out. we're going to look at an example to illustrate what is going on. So we have a tank that's has an inlet at the top and the bottom, and we want to figure out the time rate of change of the mass within the tank, as well as the inlet and exit mass flow rates. So the first thing we're going to do is fix our states. At state 1, we know our temperature and pressure. At our given pressure of 20 bar, our saturated temperature is equal to 112.4 degrees C. Our temperature is greater than our saturation temperature, which means we are a superheated vapor. So from table A4, I get our specific volume at state 1 is 0.1996 meters cubed per kilogram. So our mass flow rate at our inlet is equal to our area times our velocity divided by our specific volume, which is 10 times 10 to the minus 3 meters squared times 20 meters per second divided by 0.1996 meters cubed per kilogram. So we get that our mass flow rate is equal to 1 kilogram per second. At state 2, we have T is equal to 150 degrees Celsius and P is equal to 10 bar. Our temperature is less than our saturation temperature, so we are a compressed liquid. If you were to go to the compressed liquid tables, you would find that pressure and temperature doesn't exist. That's because we commonly approximate the properties of compressed liquids as saturated liquids. So our specific volume in state 2 is going to be approximately the specific volume of saturated liquid at 150 degrees Celsius, which equals 1.0905 times 10 to the minus 3 meters cubed per kilogram. So we get our mass flow rate at our exit is equal to 6 times 10 to the minus 3 meters squared times 1 meter per second divided by 1.0905 times 10 to the minus 3 meters cubed per kilogram, which equals 5.5 kilograms per second. To figure out the time rate change of mass within the system, we're going to use our mass balance, which tells me that the rate at which mass in the system is changing is my mass flow rate in minus my mass flow rate out, which is 1 minus 5.5, which is equal to minus 4.5 kilograms per second. The last simplification we are going to look at is what happens if we assume our system is operating at steady state. If we're operating at steady state, all of our properties do not change with time. So for a control volume at steady state, the amount of matter within the control volume doesn't change. It's fixed. So therefore, dm dt is equal to 0. So we get what comes in has to equal what goes out. You can also look at our mass flow rate in terms of local properties, where your mass is equal to the volume integral of your density times your volume. You could rewrite your mass balance in terms of volume, in terms of density and volume. However, this is not something we are explicitly going to use in this class. So we're going to look at another example of an application of a steady state mass balance. So we have a feed water heater that's operating at steady state. It has 2 inlets and 1 exit. At inlet 1, we have water vapor entering at 7 bar and 200 degrees Celsius with a mass flow rate of 40 kilograms per second. At inlet 2, we have liquid water at 7 bar and 40 degrees Celsius. And you know the area is 25 centimeters squared. Saturated liquid at 7 bar exits at 0.3 with a volumetric flow rate of 0.06 meters cubed per second. We want to determine the mass flow rate at inlet 2 and at the exit, and the velocity at inlet 2. So it's steady state. So what comes in has to equal what goes out, which means that our mass flow rate at 1 plus our mass flow rate at 2 has to equal our mass flow rate at 3. We know our mass flow rate at 1. It's given as 40 kilograms per second. Our mass flow rate at 3 is going to be our volumetric flow rate divided by our specific volume. We are given our volumetric flow rate. We just need to figure out our specific volume. So let's fix state 3. State 3 is saturated liquid at 7 bar. So from table A3, I get V3 is equal to VF, which is 1.108 times 10 to the minus 3 meters cubed per kilogram. So I get the mass flow rate at our exit is equal to 0.06 meters cubed per second divided by 1.108 times 10 to the minus 3 meters cubed per kilogram, which is equal to 54.15 kilograms per second. So from our mass balance, we get that our mass flow rate at 2 is equal to our mass flow rate at 3 minus our mass flow rate at 1, which is 54.15 minus 40, which equals 14.15 kilograms per second. The mass flow rate at 2 is going to be equal to our area times our velocity divided by our specific volume, which means our velocity is going to be equal to our mass flow rate times our specific volume divided by our area. We still need V2, sorry, our specific volume at state 2. So if we fix state 2, we have P is equal to 7 bar, T is equal to T sat, which is equal to 165.0 degrees Celsius. No, sorry, T sat is equal to that. Our temperature is less than T sat, so it's a compressed liquid, which should make sense since it said liquid water enters. So V2 is approximately VF at our temperature, which is equal to 1.0078 times 10 to the minus 3 meters cubed per kilogram. So V2 is equal to 14.15 kilograms per second times 1.0078 times 10 to the minus 3 meters cubed per kilogram divided by 25 centimeters squared times 10 to the 4 centimeters squared per meter squared. We get our velocity is 5.7 meters per second. In our next video, we are going to go over the energy balance for open systems.